Welcome to this walkthrough of LeetCode problem number 1106, parsing a Boolean expression. In this session, we'll break down the problem, explore the key challenges, and review a structured approach to solve it. Let's dive in. In this problem, you are tasked with evaluating a Boolean expression represented as a string. These expressions are composed of a few key elements. First, there are the constants true, which is represented as t, and false, represented as f. Beyond these, there are three types of operations you need to handle. The first is the not operation, written as expr, which simply inverts the truth value of the expression inside it. Next, there's the and operation, represented as and expr1, expr2, which evaluates to true only if all the inner expressions are true. Finally, there's the or operation, written as expr1 is expr2, which evaluates to true if at least one of the inner expressions is true. Your goal is to evaluate the given expression and return the result, which will always be a Boolean value, either true or false. The input is a single string representing a valid Boolean expression, and the output is the Boolean result of evaluating it. To understand how these expressions work, let's look at a couple of examples. In the first example, the input expression is f. This means we are applying the not operation to the value false. Since not inverts the truth value, this evaluates to true, which is the output. In the second example, the input expression is and t, f, t, comma, t. Here, we have both nested expressions and multiple operations. First, the inner expression and t, f, t involves an operation on the values true, false, and true. For and to evaluate to true, all the inputs must be true, but since one of them is false, the result of this is false. Now, let's break down the rest of the second example. Another inner expression, t, applies the not operation to true, which results in false. Finally, we evaluate the outer expression, false, false, which is an or operation. Since or evaluates to true if at least one of the inputs is true, and here both inputs are false, the result is false. This gives us the final output for this example, false. In the third example, the input expression is and t, f, comma, f. Let's start with the inner components. First, the expression t, f is an or operation applied to true and false. Since one of the values is true, the result here is true. Next, in the third example, we evaluate the expression f, which is a not operation applied to false. This gives us true as the result because not inverts the truth value. Finally, we look at the outer expression and true, true. This is an and operation applied to the results of the two inner expressions, both of which are true. Since and requires all inputs to be true, the overall result is true. The output for this example is therefore true. The constraints for this problem ensure the expression length is between 1 and 20,000 characters, and the input contains only valid characters such as t, f, operators, and structural symbols like parentheses and commas. Your solution should handle these efficiently, especially for large expressions, and account for edge cases such as nested expressions or minimal inputs like t. When approaching LeetCode problem number 1106, the task centers around evaluating a Boolean expression represented as a string. The expressions include constants like t and f for true and false, operators like exclamation point and, as well as parentheses for grouping. One possible approach is brute force parsing, where we process the string character by character, recursively evaluate any sub-expressions, and manually perform logical operations like not, and or. This method directly mirrors the problem's requirements but comes with inefficiencies. The recursive parsing often involves slicing substrings at every level of nesting, which can lead to a time complexity of n squared, in the worst-case scenario for deeply nested structures. While this approach is straightforward to implement, it becomes impractical for larger inputs due to its inefficiency. Alternatively, stack-based iterative parsing offers a more efficient solution. Here, we use a stack to delay evaluations until a closing parenthesis is encountered. At that point, we process the sub-expression and push the result back onto the stack. This method avoids substring slicing and achieves a linear time complexity of n, making it significantly faster. However, it does require careful implementation to manage the stack operations effectively. Another viable method is recursive parsing with index tracking. Instead of slicing substrings, this approach uses an index pointer to traverse the string and evaluate expressions directly. A helper function is typically employed to manage the parsing process, maintaining the index as it evaluates each portion of the expression. This method runs in O(n) time complexity because the string is traversed only once. Additionally, the space complexity is O(h), where h represents the maximum depth of nested parentheses, as recursion depth corresponds to the nesting level. The primary advantage here is the elimination of substring creation, making it simpler and more efficient than brute force parsing. However, it's important to note that this approach is still vulnerable to stack overflow in cases of extremely deep nesting. Among these options, the stack-based parsing strategy emerges as the most practical choice. It avoids the inefficiencies associated with brute force methods and is less prone to recursion depth issues compared to recursive parsing. By leveraging a stack, we can evaluate sub-expressions as soon as their operands and operators are fully identified, ensuring both efficiency and scalability. This method aligns well with the natural flow of evaluating Boolean expressions, especially for large or deeply nested inputs. The stack-based approach strikes an ideal balance between efficiency and robustness. Unlike brute force methods, it eliminates redundant computations and avoids the recursion depth limitations seen in recursive parsing. This makes it a practical choice for both competitive programming and real-world scenarios. A key insight that simplifies this problem is recognizing that the logical operators not, and or only require their immediate operands to be evaluated. Using a stack allows us to process these sub-expressions as soon as we encounter a closing parenthesis, which is both intuitive and efficient. Additionally, the stack naturally mirrors the structure of nested parentheses, making it a perfect fit for this type of problem. There's no need to create substrings, which was the main bottleneck in brute force approaches. In terms of complexity, this method achieves optimal results, O(n) time complexity, as each character in the string is processed exactly once, and O(n) space complexity, due to the stack used for operands and operators. By combining efficiency, scalability, and ease of implementation, the stack-based approach provides a robust solution to this problem, making it the clear choice for optimal performance. To understand this problem, we need to evaluate Boolean expressions represented as strings. The input consists of operands, operators, and parentheses. Operands are simple values like T4 true and F4 false. Operators include logical not, represented by exclamation point, and, represented by and or, represented by. Parentheses are used to group sub-expressions, which could be nested. For example, the expression tf applies the not operator to false, resulting in true. Similarly, tf evaluates the or operation on true and false, which results in true. A more complex example is and t, ft, where the and operator is applied to two sub-expressions. The goal is to parse these strings and compute their Boolean values correctly. Now, the approach to solving this problem involves recursive parsing. Recursion is a natural fit because the Boolean expression is inherently structured with nested sub-expressions. First, we identify the operator at the start of the expression, such as exclamation point or and. Next, we extract the operands, which may themselves be nested expressions enclosed in parentheses. The operator is then applied to the results of evaluating these operands. To break this down further, pre-processing is done first to remove unnecessary whitespaces, though the input is guaranteed to be valid as per the problem constraints. Then, a helper function, such as evaluate expr, is designed for recursive evaluation. If the expression is a single operand like t or f, we return true or false directly. Otherwise, for more complex cases, we identify the operator, parse the operands, and recursively evaluate each operand before applying the operator to produce the final result. For each operator, we apply its defined logic. The not operator negates its single operand, flipping true to false or false to true. The and operator returns true only when all operands evaluate to true, and the or operator returns true if at least one operand is true. Parsing operands becomes more challenging with nested expressions. To handle this, we use a stack to match parentheses, ensuring that sub-expressions are correctly grouped. After parsing and evaluating all operands, the final result is returned. For example, deeply nested cases like and tf, f require careful handling of each level of nesting. Edge cases include single operands like T or F and deeply nested expressions that test the robustness of the approach. Recursion is particularly well suited for this problem since the nested structure of the input maps directly to recursive evaluation. Matching parentheses during parsing is crucial to ensure operands are grouped correctly, and this is effectively managed using a stack. Logical operators have straightforward behaviors, such as in short-circuiting if any operand is false, which can optimize evaluation. The algorithm processes each character in the input string exactly once, resulting in a time complexity of O(n), where n is the length of the string. For space complexity, the depth of recursion corresponds to the maximum nesting of parentheses, which is O(d). Additional data structures like stacks and lists help manage intermediate states, such as storing operands during parsing or handling nested expressions. Let's walk through an example to see the algorithm in action. The input expression is AND T F, F. The main operator is AND, with two operands, the subexpression T F and the subexpression F. For the first operand, T F, the OR operator is applied to T and F. Since true or false evaluates to true, this operand results in true. For the second operand, F, the NOT operator negates false, resulting in true. Finally, the AND operator is applied to these two results, true and true, which evaluates to true. In terms of complexity, each character of the input string is processed once, giving a time complexity of O(n). The space complexity depends on the depth of nested parentheses, which determines the stack usage, and is O(d). This example demonstrates how the algorithm recursively evaluates sub-expressions to compute the final result efficiently. Here, we start with the implementation of the parseBoolExpr function inside the solution class. The function includes a nested helper function called evaluate, which is responsible for recursively processing the Boolean expression. First, the function checks if the input is a literal Boolean value, represented as T4 true or F4 false, and returns the corresponding Python Boolean values. The implementation then uses a stack to manage the parsing of the expression. As we iterate over each character in the string, an opening parenthesis indicates the start of a new group, so we append an empty list to the stack to represent this group. Conversely, when encountering a closing parenthesis, it marks the end of a group. At this point, we pop the group from the stack, as well as the operator that precedes it, and apply the operator to the group's values. Depending on whether the operator is for not and for and, or for or, we evaluate the group accordingly and push the resulting value back onto the stack. Operators and Boolean literals are also handled during the iteration, ensuring the stack is updated appropriately as we parse the expression. In cases where a Boolean literal, such as T or F, is encountered and the current stack level represents a group, the literal is added to the group by appending the evaluated value. Otherwise, the literal is simply pushed onto the stack as a standalone value. After the loop completes, the final result of the expression will remain on the stack as the only element, so we return that value. Finally, the parseBoolExpr function returns the result of calling the evaluate function on the entire Boolean expression. This design allows us to efficiently parse and evaluate any valid Boolean expression by leveraging the stack for grouping and operator precedence, ensuring correctness and clarity in the implementation. Here, we begin by defining a class solution with the main method parseBoolExpr, which takes a Boolean expression as a string input and returns the evaluated result. The parseBoolExpr method delegates the task to a helper method called evaluate, which processes the actual logic of parsing and evaluating the expression. In the evaluate method, we first handle the simplest cases. If the expression is the literal T, we return true, and if it's F, we return false. Next, we initialize a stack using a deque to help us parse and evaluate the expression in a structured manner. As we iterate through each character of the expression, when we encounter an opening parenthesis, we push a new ArrayList Boolean onto the stack. This list will temporarily store Boolean values within that group. When we encounter a closing parenthesis, it signals the end of a group. At this point, we pop the group from the stack, along with the operator that was pushed earlier. Based on the operator, we compute the result for that group. For example, if the operator is, we negate the single Boolean value in the group. If it's AND, we check if all the values in the group are true. And if it's, we check if any value in the group is true. The result is then pushed back onto the stack for further evaluation. Now, when we encounter an operator such as and, or, we simply push it onto the stack. These operators will be used later when we process their corresponding groups. For Boolean literals, t and f, we convert them into their respective Boolean values, true or false. If the top of the stack is a list, which means we are inside a group, we add the Boolean value to that list. Otherwise, we push the value directly onto the stack. This ensures that values are correctly grouped under their respective operators. Finally, after processing all the characters in the expression, the stack will contain the final evaluated result of the entire Boolean expression. We pop and return this result as the output of the evaluate method. This approach leverages the stack to handle nested structures and ensures that each operator is applied to the correct group of values, maintaining the integrity of the Boolean logic throughout the evaluation process. In this example, we are evaluating the expression f. The process begins by calling the evaluate function with the input f. At the start, the stack is empty. The first character we encounter is the e operator, which is immediately pushed onto the stack. This operator signifies a not operation. Next, the character is processed, indicating the start of a new group. To handle this, we push an empty list onto the stack to collect the elements of this group. Then, we encounter the f character, which represents a logical false. We evaluate f as false and add it to the current group, which is the empty list at the top of the stack. At this point, the stack contains the operator in the group false. Now, we process the closing parenthesis, which marks the end of the current group. To handle this, we pop the group false from the stack. Then, we also pop the operator from the stack. The operator is applied to the group false, which means we evaluate not false, resulting in true. This result is then pushed back onto the stack. At the end of the evaluation, the stack contains a single value, true. Finally, we return the top of the stack as the result of the expression, which is true. Let's consider the next example, where the expression is and, f, f. We start by calling the evaluate function with this input, and the stack is initially empty. The first character encountered is the AND operator, which represents an AND operation. This operator is then pushed onto the stack. Following that, we process the opening parenthesis, which signifies the start of a new group. To manage this group, we push an empty list onto the stack. Next, we encounter the operator, representing an OR operation. This operator is also pushed onto the stack, so the stack now contains the AND operator, an empty group, and the operator. Continuing with the expression, we process another opening parenthesis, which starts another new group. In response, we push another empty list onto the stack to collect the elements of this group. After that, we encounter the t character, which represents a logical true. We evaluate t as true and add it to the current group, which is the empty list at the top of the stack. Then, we process the f character, representing a logical false. We evaluate f as false and add it to the current group as well. At this stage, the current group contains true, false. When we process the closing parenthesis, the group true, false is popped from the stack along with the operator. The operator is applied to this group, evaluating any true, false, which results in true. The result is then pushed back onto the stack, leaving the stack with the AND operator and the value true. Next, we process the sub-expression f. As we saw earlier, this evaluates to true following the same steps. The result, true, is then pushed into the current group, which already contains true. At this point, the group becomes true, true. When the closing parenthesis is processed, the group true, true is popped along with the AND operator. The AND operator is applied to the group, evaluating all true, true, which results in true. This result is then pushed back onto the stack. At the end of this evaluation, the stack contains a single value, true. We return this value as the result of the expression, which is true. In the third example, we evaluate the expression and t. The process begins by calling the evaluate function with this input, and the stack is initially empty. The first character encountered is the operator, representing an OR operation. This operator is pushed onto the stack. Next, we process the sub-expression AND, T, F, T. To evaluate this, the AND operator is pushed onto the stack, and the values T, F, and T are collected into a group as true, false, true. Applying the AND operator to this group means evaluating all true, false, true, which results in false. This result is then added to the current group at the top of the stack, so the stack now contains false. Following that, we evaluate the sub-expression T. The T character is evaluated as true, and the operator is applied, resulting in not true, which is false. This result is added to the current group, which now contains false, false. When the closing parenthesis is processed, the group false, false is popped along with the operator. The operator is applied to the group, evaluating any false, false, which results in false. This result is then pushed back onto the stack. At the end of the evaluation, the stack contains a single value, false. We return this value as the result of the expression, which is false. The time complexity of this solution is determined by two main factors: the depth of recursion and the total number of characters in the input string. To break this down further, the algorithm processes each character in the input string exactly once during its linear traversal, which contributes O(n), where n is the length of the string. Stack operations, such as pushing and popping items, are constant time, O(1). However, when encountering a closing parenthesis, the algorithm evaluates a group of Boolean values using operations like all or any. The size of these groups can, at worst, be proportional to the input size n, meaning that such evaluations also contribute O(n). Lastly, the recursive evaluations handle characters like T or F in constant time, O(1), and the recursion depth is limited by the nesting depth of the input expression. Taken together, the overall time complexity remains O(n), as each character is processed exactly once, and all associated operations are bounded by the length of the input string. Now let's look at the space complexity. The stack plays a key role here, as it is used to track operators and groups within the expression. Each open group, denoted by a parenthesis, results in a new list being pushed onto the stack. The maximum size of the stack is determined by the nesting depth of the expression, which we denote as D. So, in the worst case, the stack size grows to O(d). Additionally, for each group, the stack temporarily stores Boolean values like T and F, or operators like AND. This memory usage is proportional to the input size, contributing O(n). Another factor is the recursive call stack, where the recursion depth is also limited by the nesting depth, contributing O(d) to the space complexity. When we combine these, the overall space complexity becomes O(d plus n), where d is the maximum nesting depth and n is the length of the input string. If there are no nested groups, meaning d equals 1, the space complexity simplifies to O(n). Next, let's analyze the best, average, and worst cases. In the best case, the expression contains no nested groups, and all Boolean values can be evaluated directly. Here, the time complexity is O(n), and the space complexity is also O(n). For average cases with moderate nesting, the time complexity remains O(n), as each character is still processed once, and the space complexity becomes O(d plus n), where d represents the nesting depth. In the worst case, we encounter deeply nested expressions, which lead to the maximum recursion depth and stack usage. Even in this scenario, the time complexity remains O(n), but the space complexity reaches O(d plus n). Comparing this approach to a brute force method, a naive solution might try generating all possible combinations of Boolean values for each sub-expression, which would result in exponential time complexity, O(2 to the power of k), where k is the number of Boolean values. In contrast, the optimized stack-based approach efficiently processes the input in linear time, O(n), avoiding redundant evaluations and ensuring space usage is proportional to the nesting depth and input size. Finally, let's solidify this understanding with a mathematical proof for the big O complexities. The time complexity is O(n), because each character in the input string is visited exactly once during the main iteration loop. Operations like stack.append and stack.pop are constant time, O(1). When evaluating groups using functions like all or any, these operations iterate through subsets of the input, but the total cost of all group evaluations is still bounded by the input size n. For space complexity, the stack grows in proportion to the nesting depth d, as each level of nesting adds to the stack size. Additionally, the recursion depth is also bounded by d, and temporary storage of input characters and Boolean values is limited by the input length n. Together, these factors yield a combined space complexity of O, d plus n. This ensures that the algorithm is not only efficient in processing time but also in its use of memory, even for deeply nested or large input expressions. When working on this problem, there are a few common mistakes to be aware of. One major issue is not handling nested expressions properly. Deeply nested Boolean expressions can be tricky, especially if parentheses are imbalanced. This often leads to runtime errors or incorrect outputs. To address this, you can use a stack-based approach. A stack allows you to evaluate sub-expressions in the correct order while ensuring that parentheses are balanced during parsing. Another common mistake involves incorrect handling of the exclamation point operator. Some implementations mistakenly apply the not operator to the entire expression instead of just the immediate operand. For example, instead of flipping only the next value, such as turning t into f, the operator might be applied too broadly. The fix here is to ensure that the exclamation point operator modifies only the next immediate value. Finally, inefficient parsing of large strings is another pitfall. Repeatedly parsing the entire expression or using inefficient string operations, such as slicing, can drastically increase time complexity. Instead, you can use an index-based approach or pre-process the string to avoid redundant computations and improve efficiency. Another mistake to watch out for is failing to handle edge cases with no operands. For instance, expressions like and, or, where there are no values inside the parentheses, can cause errors in some implementations. To handle these cases correctly, make sure to validate the input. For example, you can return true for and false for, based on the logical operations. Additionally, ignoring input constraints can lead to undefined behavior. This includes constraints such as the maximum input length, which can go up to 10 to the power of 4, or invalid characters that may appear in the input. To prevent such issues, always validate and sanitize the input before processing. This ensures that your solution is robust and adheres to the problem's requirements. Now, let's think about the problem from an interviewer's perspective. Parsing problems often require you to recognize patterns, such as using recursion or stack-based approaches. Demonstrating that you can systematically break down nested structures is key to showing your problem-solving skills. Being aware of edge cases is another critical factor. For example, handling empty operands, extremely long inputs, or deeply nested expressions can set you apart from other candidates. Interviewers might also ask about the trade-offs between recursion and iterative solutions. While recursion is often easier to implement, it carries the risk of stack overflow with deeply nested inputs. On the other hand, stack-based solutions are more robust but can be slightly more complex to implement. Additionally, you should be prepared to discuss optimization opportunities. For example, minimizing string operations and leveraging indexes can help you handle large inputs more efficiently. These insights demonstrate that you not only understand the problem but also think critically about the efficiency and robustness of your solution. To deepen your understanding, it's helpful to explore related problems that share similar concepts. For instance, LeetCode 1249, minimum remove to make valid parentheses, focuses on balancing parentheses, which is closely related to parsing nested structures. LeetCode 22, generate parentheses, involves creating valid parentheses combinations and provides insight into how recursion can be used effectively in parsing problems. Another example is LeetCode 394, decode string, which deals with parsing nested string structures, much like Boolean expression parsing. Finally, LeetCode 856, score of parentheses, involves evaluating expressions based on parentheses, which shares structural similarities with this problem. Additionally, there are alternative approaches to consider. Recursive parsing is one option where you evaluate each sub-expression by breaking it down into smaller parts. The advantage of this approach is that it's relatively easy to write and understand. However, it comes with the risk of stack overflow for deeply nested inputs, especially when the nesting depth exceeds 10 to the power of 4. Stack-based iterative parsing is another effective approach. Here, you use a stack to evaluate expressions iteratively, pushing and popping values and operators as you parse. This method is more robust compared to recursion because it avoids the risk of stack overflow, making it better suited for deeply nested inputs. However, it can be slightly more complex to implement, as you need to carefully manage the state of the stack throughout the parsing process. Another alternative is a two-pass parsing approach. In the first pass, you pre-process the input, for example, by converting it into a tree or postfix notation. In the second pass, you evaluate the processed structure. The primary advantage of this approach is that it decouples parsing from evaluation, making your solution more modular. However, it may require extra space due to pre-processing, which is a trade-off to consider. Each of these approaches has its strengths and weaknesses, and the choice depends on the specific constraints and requirements of the problem. Great work! To summarize, we explored the key steps to solve LeetCode problem number 1106 by parsing and evaluating Boolean expressions. Remember to focus on recursion and operator precedence for similar problems. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!